Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 11.5 from your textbook. In this section, we're going to be introducing ourselves to the next type of series that we want to study, which is actually based on a very special type of sequence that we introduced back in 11.1. So to begin with, let's go ahead and recall a definition from 11.1. We want to recall that an alternating sequence was a sequence of the form -1 to the n times a sub n, where that a sub n was always strictly greater than 0 for all n that was defined for our index. Remember that the reason that we had this definition where the a sub n had to be strictly greater than 0 or strictly positive was so that this -1 to the n times a sub n actually alternated. Since this was always positive, then this -1 to the n actually controlled when this was positive and negative. And remember that this -1 to the n, whenever n is even, -1 to an even exponent is going to be +1, and -1 to any odd exponent is going to be -1. So this sort of controls whether or not it's positive or negative, and then this sort of controls the size or the magnitude of each term. So that was an alternating sequence back from 11.1, and we learned how to analyze those by simply saying that if the limit of those sequences went to 0 in absolute value, then the alternating sequence converged to 0. If the limit in absolute value went anywhere else, well, then we said that the alternating sequence was actually going to diverge by oscillating or simply not existing. So, an alternating series, since we're now more interested in series than in sequences, is of course the sum of an alternating sequence. So, in other words, what we're going to be focused on studying are what we call alternating series, which are series of the form the sum -1 to the n times a sub n, where again we have that restriction that a sub n is greater than 0 for all n that we're studying. So, we're now going to be interested in trying to sum up an alternating sequence. As you can imagine, summing up something that has positive and negative terms is more complicated because you've got positive and negative terms that might be canceling out or at least reducing the size of each other. But in some ways, we would think that this is probably more likely to converge than the series that we've been studying previously. All the series that we've been studying previously, we were adding up an infinite amount of infinitesimally small things, but all of those infinitesimally small things were positive. So we were adding up an infinite amount of positive numbers, and we were trying to figure out, did that converge to a finite value or did it diverge? Here, though, this alternating piece should in some ways help the convergence, because even though we're still trying to figure out what happens when we add up an infinite amount of things, well, now some of those things are positive, some are negative, and when you add them up, they should help to cancel each other out. So we should sort of know intuitively that these alternating series have a better chance of converging. Now, it turns out that alternating series have their own sort of test. We've learned lots of tests for series already. We've talked about the test for divergence, the integral test, direct comparison test, and limit comparison test, and we'll revisit those as we proceed. But for right now, we're going to introduce a test that specifically applies to these alternating series. So we're going to talk about the alternating series test. So the alternating series test, as you can imagine, only applies when you have an alternating series. So we're going to suppose you have an alternating series of the form sum -1 to the n a sub n. You'll notice again we're not listing the subscripts or the index here because again this is going to be a test about the behavior, meaning whether or not it converges or diverges. So the starting point doesn't matter, and we know we're always going to infinity because we're interested in this class exclusively about infinite series. So again, we're just going to write that as sort of shorthand. So we have an alternating series of this form, and again, remember that means that those a sub n's always have to be strictly greater than 0. So there's two conditions that we need to check. First, if we can show that the limit as n goes to infinity of a sub n is equal to 0. Notice that this is the limit just applied to the magnitude part. We ignore this when we're doing the limit, and we just focus on the limit of those a sub n's. If we can show that that is 0, and we can show that those a sub n's are strictly decreasing, meaning that a sub n is greater than a sub n plus 1, that each time you step forward in that sequence, it gets smaller and smaller, then you automatically know that the alternating series will converge. So if you can show these two things, you immediately get that the series converges. Now, a couple notes here. If, when you're checking these two conditions, if the first condition is not met, so the limit does not equal 0, Well, then we actually know that the series will diverge, not via the alternating series test, but via the test for divergence. Remember, that was the first test for series that we discussed, and we said if the limit of the terms is ever non-zero, we immediately know that the series will diverge. So if you're checking this condition for the alternating series test and this is not satisfied, then you can actually conclude that your series diverges via the test for divergence. One small note about that, you should always remember that if this happens here, you do not say that it diverges by the alternating series test. The alternating series test either gives you no information or tells you something converges. If this first condition fails, we would then say that it diverges via the test for divergence. So very important to be able to quote the appropriate test in these situations. If condition 2 is not met, so in other words, if a sub n is not strictly decreasing, then unfortunately we get no information about the series. So if a sub n is not strictly decreasing, then the alternating series might converge or it might diverge. We actually don't know, and unfortunately we'd have to study it on a more case-by-case basis. It turns out that except for a couple examples at the very end of this video, we're not going to really run into anything where this happens because where this doesn't happen, because again, you'd have to analyze those on a case-by-case basis, and it turns out they're pretty complicated. We will see a couple examples of that right at the end of this as just to sort of show you that you really do get no information, but other than that, that's probably the only time we're going to run into it. All right, so before we get into some examples of sort of performing this alternating series test, what I would like to do is go ahead and do a quick proof of it. Now, the proof of the alternating series test is not particularly hard, but it does require sort of a clever trick. And the whole basis of the proof, which we'll do in just a moment, is all going to be based around looking at the even and odd partial sums. And the reason why that's so important is that even and odd often proves to be very important when working with things that are alternating, because on the even terms you have positive terms, and then on the odd terms you have negative terms. So oftentimes when you're having to prove something regarding alternating series, using even and odd can be sort of a helpful trick. So let's go ahead and take a look at the proof here. So for the proof, right, we get to assume, so let's just remember what we sort of assumed since it's on the previous page. So assume we have series sum minus 1 to the n, a sub n. And just for simplicity, we're going to assume that it starts from 0 and goes to infinity. Again, this is something where you can do that without loss of generality. So we're just going to assume that we start from 0. And we're going to assume that a sub n is greater than 0 for all n. So we can say that this part is always positive there. And we get to assume that the limit as n goes to infinity of a sub n equals 0. So we get to know that these terms go to 0. And we get to assume that a sub n is strictly decreasing. So we know that a sub n is always getting smaller. And we need to show that sum n equals 0 infinity minus 1 to the n, a sub n converges. So we get to assume we have this sort of series. We get to assume that the limit is going to 0. We get to assume that the terms are strictly decreasing, and we need to show that this converges. So what I'd like to do is, like I said, I'd sort of like to look at the partial sums. So I'm going to start by looking at the even partial sums. So things of the form s sub 2k. And whenever you write something like 2k or 2 times anything, you know that 2 times any number is going to be an even number. So this is an easy way of phrasing an even. So let's look at the even partial sums. Now, I could use the summation notation, but I find that that sometimes is a little tricky for people to follow. So let's actually write out what s sub 2k would be. Well, you'd start at n equals 0. Of course, n equals 0 minus 1 to the 0 would be 1, so it's positive, and you'd have a sub 0. So it would go a sub 0, and then minus a sub 1, and then plus a sub 2, and then minus a sub 3, and so on and so forth. That's what the s sub 2k would be. And of course, at the very end, it would end with minus a sub 2k minus 1, and then plus a sub 2k. So that's what the even partial sums would look like. They would sort of focus on those pieces. Okay, let's actually go ahead and even be a little bit more explicit and sort of write out the first few even partial sums. So S sub 0 would be A0. S sub 2 would be A0 minus A1 plus A2. S4 would be A0 minus A1 plus A2 minus A3 plus A4. S6 would be A0 minus A1 plus A2 minus A3 plus A4 minus A5 plus A6, etc. Okay, I think that should be enough to sort of see the idea behind this proof. So what I first want to do is I want to do a little bit of sort of clever grouping. In each of these, I'm going to sort of initially group like this. So I'm going to put some of these terms together like this. Okay, so I'm going to look at minus A1 and A2, minus 1 and A2, and then minus A3 and A4 together, minus A1 and A2, minus A3 and A4, minus A5 and A6. Now, what I hope we can all see is that these terms are always negative, since A sub n is strictly decreasing. Since A sub n is strictly decreasing, we know that A0 is greater than A1, is greater than A2, is greater than A3, so on and so forth. So if we group A1 and A2, A1 is bigger than A2, A1 is negative, so this has to be negative. A3 is bigger than A4, so minus A3 and A4, that has to be negative. A5 is bigger than A6, so minus A5 is bigger than A6. So all of these are negative. So you'll notice that the even partial sums have more and more negative terms. So this should show you that S sub 2k is decreasing. So the even partial sums are strictly decreasing. Okay, but now we're going to do a little bit of a different grouping. So I'm going to write out my same one. So S sub 0 is A sub 0. S sub 2 is A0 minus A1 plus A2. S4, A0 minus A1 plus A2 minus A3 plus A4. And then S6, A0 minus A1 plus A2 minus A3 plus A4 minus A5 plus A6, so on and so forth. Okay, now what I'd like to do, though, is I'm going to group the other way. So I'm going to take this, and then I'm going to take this piece, and this piece. Okay, and you know what? Actually, I think we're going to not really group this guy, because that guy doesn't really need to be grouped. Let's go ahead and write that more like this. Okay. There we go. Okay. Now, what I want to notice here is that these red terms are always positive, right? Because A sub 0 is bigger than A sub 1, A sub 2 is bigger than A sub 3, and A sub 4 is bigger than A sub 5. So these are always positive things. So it should be clear then that S sub 2k is always greater, since all these things are going to be positive, than whatever this last term is. So S sub 2k is greater than A sub 2k, right? I mean, in this case, it's actually equal. In this one, it's some positive plus A sub 2. In this one, it's some positives plus A sub 4. In this one, it's 3 different positive numbers plus A sub 6. Certainly, S sub 2k is greater than A sub 2k. But remember, the A's are our sequence, and we know that those are always greater than 0. They're always positive. Remember, being positive is the same as always being greater than 0. So, for these even partial sums, we have that it is strictly decreasing, and we have that they are always positive or always greater than 0. So strictly decreasing and bounded below, that's our monotonic convergence theorem. So, by the monotonic convergence theorem, S sub 2k must converge. Okay, so we now know that the partial sums, the even partial sums, are headed somewhere. Now we need to turn our attention to the odd partial sums. So we're going to do the same sort of approach, but for the odd partial sums. All right, let's go ahead and give ourselves another page here. So now consider the odd partial sums. let's try to do the same trick. So now we'd be considering like S1, which would be A0 minus A1. S3, which would be like A0 minus A1 plus A2 minus A3. S5, which would be A0 minus A1 plus A2 minus A3 plus A4 minus A5. And I think that should be enough. Okay, let's try to do the same sort of trick and see if we can do some clever grouping here. So what I'm going to do is I'm going to group these together, these together, these together. And actually, you know what? We can group these as well. Sure. Okay. If we look at that, and of course this pattern continues on, well, all the things in red, they're always going to be guaranteed to be positive. Always positive. How do we know that? Well, A0 is bigger than A1, A2 is bigger than A3, A4 is bigger than A5, so this is always positive. So that means S1 is this positive number, S3 is the same positive number plus another positive, then you've got the same 2 plus another one. That tells you that the odd partial sums are always increasing. So S sub 2k plus 1, that's how we would normally notate the odds, 2k plus 1, that's a good way of always making sure you get an odd number, is increasing. So we know that these are strictly getting larger and larger. Now if we can show that they're bounded above, in other words, if they have some upper bound, then we can go ahead and use the monotonic convergence theorem. So let's do the same sort of trick. Let's look at them again and sort of group them a different way. Okay, so same terms. Let's focus on these. This part here, then this part, and this part, this part, this part, and this part. Okay, so you should be able to see that everything in blue is always negative. This is certainly negative. A1 is bigger than A2, so this is negative. This is definitely negative. A1 is bigger than A2, so this is negative. A3 is bigger than A4, so this is negative. And A5 is negative. Okay, so these are always negative. Now again, the fact that we're able to say that these were always positive, these were always negative, relies on the fact that A sub n is strictly decreasing. That's why that condition is so important. Okay, so what we have here is that S sub 1 is A0 minus something. S sub 3 is A0 minus some stuff. S sub 5 is A0 minus some stuff. That should tell you that S sub 2k plus 1 is always less than A sub 0. Right? It's always less than the first thing, because this is the first one is the first thing minus something, then it's the first thing minus more stuff, the first thing minus even more stuff. The odd partial sums are always less than A sub 0. So the odd partial sums are increasing and they're bounded above. So by the monotonic convergence theorem, S sub 2k plus 1 converges. Okay, so we're almost done. We've now shown that the even partial sums and the odd partial sums both converge. The only question that remains is, do they converge to the same place? Because maybe they're headed two different places. In other words, our series is oscillating. That would be a problem. That would mean it doesn't converge. So now we have one last thing to show. Now we need to show that the limit as k goes to infinity of S sub 2k equals the limit as k goes to infinity of S sub 2k plus 1. That's what we need to show. If we can show that, then we know that the odd partial sums and the even partial sums are going the same place, and that guarantees that our partial sums are headed somewhere, and that means that our series converges. Because remember, the series converging is the same as the partial sums converging. So how are we going to show that? Well, it shouldn't be too hard to see that S sub 2k plus 1 is S sub 2k plus A sub 2k plus 1. This is how we always get the next partial sum. If you want this partial sum, you take the previous partial sum and add the next term. Unfortunately, that's a little off. I actually should say minus that one. because we know that a sub 2k plus 1 is going to be an odd term, which means we need to subtract it. So my apologies there. That should say minus. Okay, let's apply the limit on both sides. Why are we allowed to apply the limit? Because we know that all of these things converge now. That's why we did that work ahead of time. So the limit as k goes to infinity, s sub 2k plus 1, is the limit as k goes to infinity, s sub 2k, minus the limit as k goes to infinity, a sub 2k plus 1. Okay, now, the last thing we need here is the other assumption that we made. If we look back, so far we have made a lot of use of this assumption here, that it is strictly decreasing. We also made use of this one time to know that all the terms were greater than 0. That's actually how we got this little piece here. One thing we haven't used, though, we haven't used this, that the limit is headed to 0. Now we use that. Since the limit is headed to 0, we know that this must be going to 0 because the sequence approaches 0. So we get the limit as k goes to infinity, s sub 2k plus 1 is the limit as k goes to infinity, s sub 2k minus 0 by our assumption. And that gives us the limit as k goes to infinity, s sub 2k plus 1 is the limit as k goes to infinity, s sub 2k. So odd, even partial sums converge to same value, so series converges. Check. QED. So this is a pretty advanced proof. You guys would not be expected to sort of recreate something on this level, but I think the ideas in it are worth thinking about, right? The main points here was that we initially started by looking at the even and odd partial sums. And the reason we broke that in is because the even and odd partial sums were easier to understand because we knew that, for example, the even partial sums always ended with a plus, whereas the odd partial sums always ended with a minus. Then we used two applications of the monotonic convergence theorem. For the even partial sums, we showed that they were getting smaller and smaller, but they were always positive. Smaller and smaller and always positive, or smaller and smaller and bounded below by 0, meant that the even ones converged. Then over here, we showed that the odd ones were getting bigger and bigger, but they never got as big as just the very first term. So they were getting bigger and bigger, bounded above by a value. That meant that they converged. So we knew that the odd sums were headed somewhere, and we knew that the even sums were headed somewhere. Then we just had to show that they were headed to the same place. So we were allowed to apply the limit because we knew that the limit existed. We used the fact that the next partial sum was the previous one plus the next term. Now we had to be careful, and I misspoke when I originally put it down. The plus of the next term, since the next term is odd, is actually a subtraction, so it was a minus there. But it didn't matter because once we applied the limit of the terms, the limit of the sequence, is headed to 0. So this limit was 0, and we got that the odd and even partial sums were headed to the same place. So, again, not going to need to recreate this proof, but I think the idea is, especially the use of that monotonic convergence theorem, like I said back in 11.1, we use that so much for so many of these theoretical results, and this proof actually uses it twice. Okay, let's turn our attention now to analyzing some actual alternating series using this alternating series test. So, here's an alternating series that we want to determine if it converges or diverges. So we have the sum from n equals 1 to infinity minus 1 to the n, 1 over n. Now, we might be tempted and say, oh, I know that the sum of 1 over n, right, that's a divergent p-series. We called that the harmonic series. So does that mean that this automatically diverges? Well, the big difference here is this has minus 1 to the n in it. Whereas the sum 1 over n is going like 1 plus a half plus a third plus a fourth plus dot dot dot, and we actually showed that that went to positive infinity. We did that via like integral test, right? That's headed to positive infinity. But this guy's a little different. This is actually minus 1 plus a half minus a third plus a fourth minus a fifth, so on and so forth. So notice that, these negatives are canceling with these positive terms. They're not canceling out completely, but they're reducing in magnitude. So this has a better shot at converging than the one that doesn't have that minus 1 to the n in it. So how do we analyze this? Well, we use the alternating series test, which we will often abbreviate as AST. What we're going to first do is we're going to look at the limit as n goes to infinity of the a sub n. The a sub n is the magnitudes. It ignores this piece here. That's just the alternating component. So we look at the limit as n goes to infinity of 1 over n. We definitely know that that goes to 0. Check. That's the first condition. The second thing is we need a sub n to be strictly decreasing. We could look at the corresponding function, f of x equals 1 over x, and take the derivative, but there's no need to. 1 over n is obviously decreasing. It is a number, 1, over something that gets larger and larger. That is a guaranteed decrease, and that's sufficient for us. The only time we need to pull out that derivative technique is if both the numerator and denominator were getting larger in size. In this case, check. So we have that the limit is 0. We have that the sequence is strictly decreasing. So we can say by AST, sum n equals 1 to infinity, minus 1 to the n, 1 over n, converges. So notice that it acts completely differently than the positive version, sum 1 over n, which we know diverges. That minus 1 over to n, minus 1 to the n, helps it out enough. There's enough cancellations between the terms that this will actually sum up to a value. All right, let's go ahead and take a look at another one. So we want to determine if this series converges or diverges. So we have the sum from n equals 3 to infinity, minus 1 to the n squared over e to the n. Once again, it is alternating, so we will use the AST. You might be thinking, wow, the AST seems pretty nice. I like that it has 2 easy conditions. Why didn't we use that beforehand back in like 11.3 or 11.4? Well, keep in mind that everything we did in 11.3 and 11.4 always had always positive terms. In other words, it wasn't alternating. So it should go without saying, but just to reiterate, the alternating series test applies when we have an alternating series. If you don't have an alternating series, you can't use this test. It must have that alternating component. For now, though, we'll go ahead and do the first thing, which is we need to check what happens with the limit as n goes to infinity, n squared over e to the n. This is polynomial and this is exponential, so we probably want to use L'Hopital because they're different sort of types of functions. So that does mean that we need to go ahead and use a replacement theorem. So we need to view this in terms of the continuous variable x. Then we can go ahead and apply L'Hopital and take the derivative of the top and bottom separately. So 2 over 2x and e to the x. And then L'Hopital again, which I guess I'll put down here. We get limit x goes to infinity, 2 over e to the x. Unsurprisingly then, 2 divided by something that goes to infinity, that is going to equal 0. We should have already known that back here. We know that exponentials are a whole level faster than polynomials. So of course, a polynomial divided by an exponential is going to go to 0. So we've got our first condition satisfied. For 2, we need to know if an is strictly decreasing. Unfortunately, we can't just say it's a number over something that gets larger, because the n squared is also getting larger. It's going like 9, 16, 25, 36, so on. So both these are going up faster and faster. So we have to look at the derivative. To do that, we need to consider the corresponding function. So consider f of x equals x squared over e to the x, or if you prefer, x squared e to the minus x. Then the derivative, which would be a product rule. If I left it like this, I'd have to do quotient rule. Nothing wrong with that, but it could be messier, so I'll use the product rule. 2x e to the minus x squared e to the minus x. Or if you prefer, I guess that would be 2x minus x squared over e to the x. Whatever you like. Now, what do we notice here? Well, remember, we're working from 3 to infinity. Starting at 3, you'd have something like 6 minus 9. That's going to be negative up top. And actually, for any other x value, as x gets larger, this is always going to be larger than this. So this is always going to be less than 0 on 3 to infinity. So that's exactly what we want. Remember, a derivative that is negative tells us that what we're looking at is decreasing. So we're all good there. So we have a limit that is 0, and the terms are getting smaller and smaller. So those are the two conditions we need. So we would say by AST, this series converges. This was a little bit more work because we had to use the replacement theorem in L'Hopital to get that the limit was 0, and we had to use the corresponding function and its derivative to show that it was decreasing, but it's the same logic as the previous one. Okay, let's take a look at another then. Let's try to determine if this series converges or diverges, still alternating. Now we have 4n squared plus 5 over 8n squared plus 1. So let's go ahead and look at condition 1 here. So we'll take the limit as n goes to infinity, 4n squared plus 5 over 8n squared plus 1. This is polynomial over polynomial. You could replacement theorem it, but it's unnecessary. You can just do 1 over n squared on top and bottom. So we get 4 plus 5 over n squared and 8 plus 1 over n squared. And then these terms, of course, go to 0. So we should get 4 over 8, which is 1/2. You will immediately notice that that is not equal to 0. So that tells us, well, it tells us that it diverges. But it doesn't tell us that by the AST. Instead, what we would say is by test for divergence, since the limit as n goes to infinity of a sub n doesn't equal 0, this series diverges. So even though we were doing this condition in hopes of using the AST, the fact that it didn't come out as 0 tells us that the series diverges, but by a different test. It is absolutely incorrect if you said by AST. The AST is a test that either doesn't give you information or tells you something converges. It never results in an idea of divergence. The reason that this one diverges is by the test for divergence. So, nice and easy problem, but just got to be very careful that you use the correct language to explain why. All right, let's take a look at one more of these. So, we want to determine if this series converges or diverges. Minus 1 to the n over n to the 4th plus 1. So, same idea, right? We should probably try to use the AST because this is certainly alternating. We do our first condition, limit n goes to infinity, n over n to the 4th plus 1. We could multiply top and bottom by 1 over n to the 4th. I should get limit as n goes to infinity, 1 over n cubed, 1 plus 1 over n to the 4th. Should be clear that that's 0, and we're all good with condition 1. For condition 2, we need to show that an is decreasing. Once again, we can sort of guess that n to the 4th is going to increase a lot faster than n, so the overall fractions or the overall quotients should get smaller. But we need to justify that using the derivative. So let's consider f of x equals x over x to the 4th plus 1. To take the derivative, this time we can't avoid quotient rule. So x to the 4th plus 1 minus, and then x times 4x cubed over x to the 4th plus 1 squared. That tells us that f prime looks like we get 1 minus 3x to the 4th over x to the 4th plus 1 squared. Now, you can imagine we're working from 1 to infinity. This is going to start at minus 3 and gets larger and larger, so this is definitely going to be negative up top. The good thing about quotient rule is it always squares the denominator, so the denominator is always going to be positive. If you have a negative divided by a positive, it's definitely going to be negative. So this is always less than 0 on our interval 1 to infinity. Check. So we now know that it's going to 0 and it is strictly decreasing, so we can say by AST, this series converges. Okay. Now, we have one last thing to do in this video, which is that I promised a couple sort of weirder examples to investigate what happens when this second condition isn't satisfied, and we are going to do those in one moment. But before we get to those, I do want to cross-compare, because this is going to sort of motivate what we're going to be doing in 11.6, what we just saw in this example versus our very first one. So let's go back and take a look at our very first example. In our very first example, we used the AST. It was very nice and easy, and we saw that it converged. But when we did that, we sort of commented that if that minus 1 to the n hadn't been there, and we had actually just looked at the sum of 1 over n, that would have diverged. So I'm just going to make a little note of that. Right? We're just going to make a note here. Note, sum 1 over n would diverge. Right? If it didn't have that alternating piece, it would have diverged. Our alternating one certainly converges, but if it didn't have that, it would have diverged. Let's go ahead and think about that for the very last one that we did. What would have happened if this hadn't had that minus 1 to the n? Well, if you think about it, if we had actually had sum n over n to the fourth plus 1, it probably wouldn't be hard to use something like an LCT to compare that to 1 over n cubed. Why 1 over n cubed? Well, let's be honest. In the long run, how much does that plus 1 really matter? If you're at 100 and you're doing 100 to the fourth, which is 1 with 8 zeros after it, do you really care about adding 1 to it? Probably not. So this doesn't really matter, and n divided by n to the fourth is 1 over n cubed. So you on your own can check that the LCT really does work here. But if this acts like 1 over n cubed, then this would converge. So even if this hadn't had the minus 1 to the n, it would have still converged. This is what we're going to be investigating in 11.6. We're going to talk about things that are what are called conditionally convergent versus absolutely convergent. Something like this is what we call conditionally convergent. This thing here is conditionally convergent. And we'll define this more formally in 11.6, but I just wanted you guys to sort of hear the words before we got there. The reason that this is called conditionally convergent is that this series does converge. But if you were to put it in absolute value, aka if you were to remove that minus 1 to the n, then it would diverge. So it is a convergent series, but it's conditionally convergent since it's depending on that minus 1 to the n to actually get it to converge. Something like this here at the end, well, even if we had gotten rid of that minus 1 to the n, in other words, even if we had put it in absolute value, it would still converge. This is often referenced as what is called an absolutely convergent series, meaning it converges and it would converge even if it didn't have that minus 1 to the n. In 11.6, that's what we're going to be studying, things that are absolutely convergent versus conditionally convergent. For now, though, before we get to 11.6, there's one last thing to do in this section, which is to talk a little bit about the very special circumstances when this second condition doesn't fail. Again, computationally for you guys, you're either going to run into things like this example, where both conditions are satisfied and you can say that it converges, or you might occasionally run into things like this, where the first condition fails and you can still get a conclusion since the test for divergence will help you out. But we should at least talk a little bit about what happens with the second condition when it fails. So we're going to look at two very unique examples. So we're going to consider this sequence. A sub n is 1 over n when n is odd, and 1 over n squared when n is even. And I want to try to determine if the sum from n equals 1 to infinity minus 1 to the n a sub n converges or diverges. So this is something we've never really seen before. This is a piecewise sequence. You have two different formulas depending on if you're on an odd or even term. But let's just take a look at first just writing out a few of the elements. So if we were to actually write out the first few pieces of this, what we're really doing in this one is we'd start with n equals 1, which is odd, so we'd use this, and of course it would be negative. So we would have negative 1 over 1. Then we'd be on an even, so we would use this, and it would be positive. So we would have 1 over 4. Then we'd be on an odd, and we'd have minus 1 over 3. Then plus 1 over 16. Then minus 1 over 5. Then plus 1 over 36, etc. That's what this thing is actually doing, where you can see that the odd ones are all negative, because of course the minus 1 to the n will be negative, and they're all just based on 1 over n. And the even ones are all positive, because when this is even, this will be positive, and they're all based on 1 over n squared. Okay. Now, you should be able to easily see here that the limit as n goes to infinity, a sub n equals 0. If we're considering the AST, let's just write out what we're doing there. If we consider the AST, the limit as n goes to infinity of a sub n certainly equals 0. I'm not going to really say much about that, but it should be clear. Doesn't matter which of the two I'm following. As n goes to infinity, both of these are headed to 0. The overall sequence is headed to 0. But 2, a sub n decreasing, that's absolutely incorrect, right? If we have 1 over 1 and then 1 over 4, that's a decrease. But then the next term was 1 over 3. That's an increase. Then 1 over 16, that's a decrease. Then 1 over 5, that's actually an increase. So this, absolutely not true. So condition 2 is failed. So AST doesn't apply. So unfortunately, we can't use the test we just learned about. So what actually happens with this series, though? Well, it's a little tricky, but it shouldn't be too hard to sort of see that this series actually is going to diverge. Why is that? Well, as sum n equals 1 to infinity minus 1 to the n a sub n diverges to negative infinity, since we actually know that the sum of 1 over n diverges, but sum 1 over n squared converges. Now, I'm not going to write this out too much because, again, this is a very sort of unique example. We're not going to run into this too much, but I would like to just explain it. The reason that we know that this diverges is because we know that 1 over n diverges, but 1 over n squared converges. So if you look back at how we define this, the 1 over n, the odds, the negatives, these things are headed, and when we're adding them up, just adding up those negatives, those are adding up to something that is a larger and larger negative number, meaning it's headed to negative infinity. But 1 over n squared, we know, is a convergent series. So 1/4 plus 1/16 plus 1/36, that's adding up to a finite positive number. So if you're taking an infinite amount of negatives and adding them up to a finite positive, well, that's going to come out as an infinite negative still. So this thing is going to diverge. And that's because one of its component, the negative ones, is going to diverge, but the positive ones are just going to add up to a finite piece that's not going to be able to take care of the massive amount of negatives that we're going to get. So this is an example of something where the AST doesn't apply, but it went ahead and diverged. Okay, let's compare this with a very, very similar example. So now we're going to consider the sequence a sub n 1 over n cubed if n is odd, 1 over n squared if n is even. So again, just to help us sort of think about that, I'm going to go ahead and write out the first few terms here. So first one, odd, because n equals 1, we'd have minus 1 over 1, then plus 1/4, then minus 1 over 27, because we would be on n equals 3, and 3 cubed is 27. Then plus 1 over 16, then minus 1 over 125, then plus 1 over 36, so on and so forth. Okay, let's try AST again. So again, it should be very clear that the limit as n goes to infinity, a sub n equals 0. Doesn't matter which of these two you're following, or if you're following both, these terms are certainly headed to 0. What about a sub n decreasing? Well, unfortunately, it's not true, because if you look at the terms, 1 over 1 to 1/4, that's a decrease. 1/4 to 1 over 27, that's a decrease. Okay, things are looking good. 1 over 16, that's actually an increase. Then 1 over 125, that's a decrease. But then back up to 1 over 36, that's an increase. Okay, so the second condition, once again, is not satisfied. So AST does not apply. Okay, so once again, the AST does not apply here. But unlike the previous one, this time, sum n equals 1 to infinity minus 1 to the n a sub n actually converges. How do I know that this one converges unlike the other? Because each piece is convergent. The odds are based on the sum of 1 over n cubed, which is convergent, and the evens are based on the sum of 1 over n squared, which is also convergent. Since sum 1 over n cubed and sum 1 over n squared both converge. And we know they both converge because they converge as p-series. So what we're basically saying here is that the odd numbers, they're all negative, but all of these are adding up to some finite negative number, and all of these are adding up to some finite positive number. Put those two together, it's still going to be some finite number. So this time it actually does converge. And the reason I wanted you guys to take the time to see these couple examples, even though we didn't, formally prove all this stuff or whatever, is mainly because this shows you that if that second condition fails, you get no information. Here's an example where the second condition failed, but it went ahead and diverged. And here's an example where that second condition failed, but it actually went ahead and converges. So unfortunately, if that second condition fails, we don't get any information from the AST. So this sort of wraps up our discussion of alternating series by themselves. We're still going to be investigating them, though, because as I mentioned, our next section, 11.6, is going to introduce us to the concept of absolute and conditional convergence.